In this video, we're going to look at dividing radicals. This is actually kind of a funny topic. Basically, at this point, what we're going to look at is trying to simplify fractions that involve radicals. And we'll extend that a little bit in the future to rationalizing numerators or denominators, which is really a trick that's all about moving radicals from the top to the bottom of fractions or vice versa. But for now, it's just this idea of trying to reduce fractions that involve radicals. So just like we have the product property for square roots, we can also write out a quotient property for square roots. And it's the exact same idea. Our exponent rules tell us if we raise a fraction to a power, that we can split that up and raise the top of the fraction, the numerator, to the power and the denominator to the power separately. And we now know that roots really are just the same thing as rational exponents, so the exponent rules apply. So if we have the square root of a fraction, we can split that up. And if we have a fraction with two separate square roots, we can combine that. And we'll use both of those to try and reduce some of these fractions. So we'll look at both ways. Sometimes one helps and sometimes the other does. So for this first fraction, you can see that it's two separate fractions. So we'll go ahead and combine that together. I will say that's not the only way to simplify this. You could extract roots from the 125, and then you would be able to cancel after you are done with that. So that would lead us to a good answer as well. But we're going to look at it this way just to practice with this property. So the reason it's helpful to combine the roots is now we can just work on the fraction underneath the root and not have to worry about that being separated by a fraction bar. So what I'm looking at here is just that I can cancel a 5 out of the top and the bottom. 5 goes into 5 once, and 5 goes into 125 25 times. Again, if you need to double check that division with a calculator to make sure you're doing it right, no problem, but try to avoid having the calculators do the root simplification and some of the more sophisticated stuff. That's what we're trying to practice and learn. So I end up with the square root of 1 over 25, and I can actually do even better with that one. Sometimes I might not get much further, but we can take the square root of 125. We're asking what do we square to get 1 over 25, and the answer is going to be 1/5. 1/5 times 1/5 is 1 over 25. So there's one example, and there'll be some variety here. The next one is similar. It just works out a little bit differently with how the fraction looks when you're done. And this one maybe even is a little simpler than the first one. If we combine the radicals, and remember you can do that with multiplication or division, not with addition subtraction. The way I think about this is we have our order of operations, our PEMDAS. And when operations are really close together on this, like exponents and multiplication or division, they play together fairly nicely. The further apart they get, the more trouble we have. So exponents to addition, subtraction, that starts to get pretty messy if we're not careful. So we don't like that mix. Combining the square roots helps me a little bit because now I can just worry about the fraction and I can say, well, 50 divided by 2, I actually know what that is. That's 25. And now I can focus back on the square root, and it's a much easier question. Square root of 25 is 5, so kind of closely related to the last problem. Okay, let's continue. Here, if we combine the two roots together, we get 60 over 12. And 60 over 12 is 5, in which case I'm done. So I wanted to show you somewhere you can actually evaluate the root. That's always really satisfying. Feels like you've really done a good job of simplifying, but sometimes you just can't do it. And if you can't actually evaluate the root, check to see if you can extract some roots, if you can simplify it a little. But 5 is prime, so I'm not going to get at any factors of 5 that are perfect squares. So I'm totally done with that one. Okay, one more like this, and then we'll work on going the other way. If I combine the roots, 11 over 55, I can cancel an 11 out. So 11 divides into 11 once, and 11 divides into 55 5 times. And this again is not a perfect square, but this is the case that's like the problems we'll do down below, where I think it would actually be worth splitting that back up. And you don't have to write this in between step if you start to see what's happening here and feel comfortable. but the rule says we could split that into root 1 over root 5, and the reason I think that's helpful is the root 1 is a perfect square. 1 is the perfect square, so the square root of 1 is 1, and I can at least write it without the top of the fraction under the root, which I would say is an improvement. It is a simplification. What you'll find is that in a lot of algebra books, and sometimes even through pre-calculus, a big deal is made about rationalizing the denominator, which means making sure there's no square roots in denominators or cube roots or whatever. The truth is there's not really a good reason for that anymore. In calculus, there's a really good reason to make sure there's no radicals in the numerator of fractions. But for now, we're just practicing the skill. So I would say I think it's a definite improvement to have any part of the fraction not be under a square root anymore. So if you can make that happen, do it. Again, we have a root 5 in the bottom. If I could extract a perfect square out of that, I would, but I can't. So this is as far as I'll go. Okay, let's see what we have down below. The square root of 5 over 36. So I can't reduce that at all. I'm not going to get very far with just simplifying the fraction, but I do see that that 36 is a perfect square. So just like in the last problem, sometimes you can actually simplify a little bit if you split the square root up. We can say root 5 is what it is. I can't do any better. But root 36 is plain old 6, and that is a little bit nicer. So root 5/6 would be considered a little bit simpler than the square root of 5/36. If you can split up any part of the fraction and get it out of the root, do it. Next, I have the square root of 32 over 25, and that's similar, but I think this is going to get a little bit messier. So I can split it up into root 32 over root 25, and I like that because the 25 is a perfect square, so I can make it root 32 over 5. However, I am not done this time because I think I can probably separate a perfect square out of that 32. So I'm going to think about that. And as usual, you can make your entire factor tree if you're having a hard time spotting it. But I'm spotting it here. So I'm going to say 32 is 16 times 2, and 16 is a perfect square. So I'll split that into root 16 times root 2. And root 16 is 4, so I can break this down to 4 root 2 over 5. And these can feel a little bit funny. Is it really simpler to have 4 times the square root of 2 over 5 than just a single square root of 32 over 25? And the answer is it depends. But for our purposes, we're really going to focus on getting as much stuff out of the root as we can. That's going to be our big goal. Okay, last but not least, root 64 over 15. So I do see the perfect square in the top. And the square root of 64 is 8. So I can get myself fairly quickly to 8 over root 15. And this is good. And for the purposes of this section, you can stop here. But I do want to show you one of our next goals that's going to come up fairly quickly is how would we get the root out of the bottom if we don't want that? The other two problems on this line ended up with no radicals in the bottom, and that is going to be a goal of ours. And the answer is you get rid of square roots by squaring, but we can't just square this entire fraction or it'll have a totally different value. If you square 5, you get 25. That's not the same number anymore, and we want it to be the same number, just written in a way that doesn't have radicals in the bottom. Remember that squaring really just means multiplying something by itself. So we can do that if we're very careful about it, as long as we do the top and the bottom. What we've really done is multiply by 1. Root 15 over root 15 is 1. Multiplying by 1 does not change the value. So this will help us succeed in our mission of rewriting this thing without roots in the bottom, but not changing its value. So now we have 8 root 15 over 15. So we'll come back to it. For now in this section, I don't really mind if you have the radicals in the bottom. If you run into a homework problem and the system is picking on you about that, let me know and I'll fix it. I think I've caught all of those, but we'll continue toward that from here. Thanks for watching.